Okay, so you sent us this really interesting video, Professor Soy's C++ introduction. And that's what we're going to dive into today.
Yeah, it's a great starting point.
Our mission here really is to pull out the core ideas, the absolute fundamentals of programming, specifically C++ day from that video. And, make it clear and interesting no matter your background.
Exactly. We're aiming for the essence. Think of it as, well, getting the key building blocks without maybe watching the whole lecture series right away.
Right.
And Professor Soy breaks it down nicely. We'll look at three main things he covers. First, the computer system itself, hardware, software, the basic parts.
Okay.
Then how we actually talk to computers, the whole evolution of computer languages leading up to C++F.
Makes sense.
And finally, how programmers actually, solve problems, the thinking process.
All right, sounds like a plan. Let's kick things off with that foundation, the computer system. Professor Soy splits it into hardware and software. Hardware first, the physical stuff.
Yeah, the bits you can, actually touch. And the star player there is the CPU, the central processing unit.
The brain. Right, that's what everyone calls it.
Pretty much, and for good reason. Its job is calculations, both arithmetic, like adding numbers, and logic, making those true-false decisions.
And Professor Soy mentioned it's often the most expensive part.
Often, yeah. Which really tells you something about its importance and, well, its complexity. All the really heavy lifting happens there.
Okay, so the CPU is the powerhouse. But it needs somewhere to work.
Right.
It doesn't just float in space. That brings us to RAM.
Exactly. Random access memory. Think of it as the CPU's superfast temporary workspace. Professor Tsoi highlights that direct connection.
So how does that work, like with his 1+1 example?
Right. So you type 1 plus 1. Those numbers and the instruction to add them, they get loaded into RAM first.
Oh.
The CPU grabs them from RAM, does the math really quickly, and the answer, too, gets put back into RAM just for a moment before it, say, shows up on your screen.
Ah, okay, so it's like a scratch pad. Fast, but not permanent.
Precisely. If the power goes out, poof, whatever's in RAM is gone. That's crucial. That's why we need secondary storage, hard drives, SSDs for keeping things long-term.
Got it. RAM for speed, secondary storage for permanence, and obviously input-output stuff, keyboards, monitors, printers.
Right, how we get info in and out.
Professor Soy also mentioned memory cells in RAM. It's not just one big pool.
No, it's more like a huge grid of tiny boxes. Each little box or memory cell has its own unique address.
Like a mailbox number.
Exactly like that. So the CPU can say, I need the data stored at address 1001, and it can find it instantly. That organization is key.
Okay, that covers the hardware pretty well. But hardware needs instructions. That's where software comes in.
Yep. And all software, as Professor Soy points out, is written using programming languages. He splits software into two main kinds.
System programs first.
Right. These are the managers. They run the computer itself. The biggest example is the operating system, Windows, Mac OS, Linux.
And he recommended Windows 10 with Visual Studio for C++.
Yeah, a practical tip for his students, likely because that's what they use in the course. Makes sense. Also, utility programs fit here, like disk cleanup tools, antivirus, stuff that keeps the system healthy.
Okay, the behind-the-scenes crew, then the other type.
Application programs. These are the ones we, as users, interact with directly to do stuff.
Like word processors.
Exactly. His example was perfect. Think about writing papers before word processors. Application software helps us complete specific tasks, makes things easier, or enables new things entirely.
Okay, hardware and software covered. Now, how do we actually tell this hardware what to do? Professor Soy starts at the very bottom. Machine language. Just ones and zeros.
With the bedrock, yeah. Fundamentally, computers only understand electrical charge or no charge. We represent that as 1 or 0, binary code.
So every single thing a computer does boils down to that.
Every single thing, no matter how complex it looks on screen, underneath it's all sequences of 1s and 0s. It's kind of mind-blowing when you think about it.
It really is.
Yeah.
So a single 1 or 0 is a bit. And binary code is just strings of these bits. But how does that become, the letter A or a spacebar press?
Ah, good question. That's where encoding schemes come in. They're basically dictionaries, agreed upon standards that map patterns of bits to characters.
Okay.
Professor Soy mentioned ASCII, that's a common one, uses 7 bits. Like 0100000001 means capital A in ASCII.
Right.
But ASCII is mostly for English. So then you have Unicode, which uses more bits, 16 usually. It can represent characters from, well, pretty much any language on Earth. Much more versatile.
So encoding schemes are the translation layer for text, but thankfully we don't usually type in ones and zeros. Professor Soy explains the evolution away from that, right?
Oh, absolutely. Imagine writing a whole program in binary. It would be incredibly slow and super easy to make mistakes.
I can't even picture it.
So the next step up was assembly language. Instead of 100110, you might write something like ADD. These short, easier to remember codes are called mnemonics.
Okay, that's better. But the computer still doesn't understand ADD, does it?
Nope, still needs translating. So you need another program called an assembler to turn that assembly code back into the ones and zeros the machine understands. It's closer to the hardware, but still a step removed from pure binary.
All right, assembly is one step up. Then came the high-level languages, like C++, Garc.
Exactly. Languages like BASIC, COBOL, Fortran, C, and yes, C++A, Java.
Mhm.
These were designed to be much closer to human language, more like English, using words and familiar mathematical notation.
Making it easier for us humans to write and read the code.
That's the whole idea. But again, the computer still only understands machine code.
So another translator needed.
Yep. For high-level languages, this translator is called a compiler. It takes your C++ code, for example, and does a more complex translation process to produce the equivalent machine code.
So assembler for assembly language, compiler for high-level languages like C++, both end up producing machine code.
You got it. And C++ sits firmly in that high-level category, compiled down to machine instructions.
That makes the whole process seem much less magical and more, well, logical. Okay, final big area from the video. Problem solving. Programming isn't just about knowing the language.
Not at all. At its heart, Professor Soy emphasizes programming is about solving problems. There's a standard technique he outlines.
Which is?
First, you really dig into the problem, analyze it, understand exactly what needs to be done. Then you outline the requirements for a successful solution. And crucially, you design an algorithm.
Algorithm. Sounds technical, but it's just a plan.
Basically, yeah.
Yeah.
It's just a precise step-by-step sequence of instructions to solve the problem or achieve the goal, like a recipe.
And he broke the whole programming process down into 3 main steps incorporating that.
Right. Step 1, analyze the problem, define requirements, design the algorithm. That's the thinking part. Step 2, implement the algorithm. This is where you actually write the code in a language like C++ Vue. And importantly, you test to verify that it actually works as intended.
Debugging, basically.
Yep, finding and fixing errors. And step 3, maintain the program. This means using it, modifying it if requirements change, fixing bugs that pop up later. It's often an ongoing thing.
He used that study time calculation as a simple example for algorithm design. How did that go again?
Yeah, it was a good, clear example. Step 1, get the input, the number of credit hours for the class. Let's say it's 3.
Oh.
Step 2, apply the rule, multiply the credit hours by the recommended study time per credit hour. Use 2 hours per credit, so 3 times 2.
Which is 6.
Exactly. Step 3, the result, 6 hours, is the output, the recommended weekly study time. That sequence is the algorithm.
Simple but effective. And then he mentioned you'd code that in C++ using Visual Studio, test it, maybe add features later, like calculating total study time.
Right, illustrating the implementation and maintenance steps too.
Now, he also mentioned 2 main approaches, or methodologies, for programming. Structured and object-oriented.
Yeah, 2 broad ways of thinking about organizing your solution. Structured programming is about breaking a big problem down.
Divide and conquer.
Pretty much. You decompose the problem into smaller, more manageable subproblems, solve each subproblem, maybe as a separate function or module, and then combine those solutions. He mentioned top-down, start big, break it down, and bottom-up, build small pieces, then assemble.
Okay, that makes sense.
Eh.
What about object-oriented programming, or OOP?
OOP takes a different initial focus. Instead of breaking down the process, you first identify the objects or the key components involved in the solution.
Objects, like real-world things.
Sometimes, yeah, or conceptual things. The key idea is that an object bundles together 2 things: data, information about the object, and operations, things the object can do or that can be done to it.
Can you give an example?
Sure. Think about representing a user account in a system. The user object might have data like username, password, email address, and it might have operations like login, logout, change password.
So the data and the actions are kept together in one package.
Exactly. And an OOP program, like one written in C++, is essentially a collection of these objects interacting with each other to get the job done. C++ is a classic example of an OOP language.
Got it. Structured breaks down the task. OOP builds up interacting components. Two different ways to approach complexity.
Precisely. Understanding both is really valuable.
So wrapping up our deep dive based on Professor Toy's intro, we've covered the basic anatomy of a computer, the hardware like CPU and RAM, and the software managing it all.
Uh-huh. Then we traced how we communicate, from those fundamental ones and zeros of machine code, through assembly, up to high-level languages like C++ that use compilers.
And finally, we looked at programming as problem solving, defining algorithms, and the difference between structured and object-oriented approaches.
Yeah, those are really the foundational pillars. Getting a handle on these gives you a much clearer picture of what programming is all about. It's not magic, it's logic.
Absolutely. It provides a solid base for anyone curious about this field.
Definitely takes away some of the intimidation factor, I think.
It really does. Thinking about how even simple things we do on a computer depend on this incredibly detailed interaction
Hmm.
between hardware components and layers of software, it makes you wonder, what other complex systems out there, things that seem almost impossibly intricate, might actually be built on surprisingly simple, logical rules if you just peel back the layers?
That's a great question to ponder.
Yeah.
Something to think about, for sure.